My name is Lawrence Harrington.
Hi, my name is Rachel Sosa.
Hi, I'm Oscar Lizondo, and this is our presentation on sketching and explaining derivatives. Our references for this were Khan Academy, the textbook, and some YouTube videos. A fun fact about sketching and explaining derivatives is the process of finding a derivative is called differentiation, and the reverse process is called anti-differentiation. For part A, it asks how is the definition of a derivative relative to the instant velocity at the point t of 1. And for that, I wrote down the definition of a derivative, which is the formula if f prime of a, if there is an f prime of a and a is equal to x, it would equal the limit as h approaches 0, or the distance between the 2 points, or points for x and y, or points for x and x prime, and it would be f of a plus h minus f of a over h. And for this equation, since our point A is 1, we would have f prime of 1 equals the limit as h approaches 0 of 1 plus h minus 1 over h. The 1s would cancel out, giving us h over h, which would be equal to 1. The definition of a derivative, or the formula up here, is the slope of a tangent line, or the instantaneous rate of change at that point, that specific point that it gives us. And for on the graph, you can see the change in y over the change in x. X plus h would represent the point differential between 2 points, which would be the slope of our secant line. But as the secant line, or the slope of the secant line, or the point, I should say, the secant line gets closer and closer and closer to our x value, the secant line would get smaller and smaller and smaller. And as we got, say, infinitely close to our point, or as it says in the limit, as h, the distance between the 2 points, approaches 0, that would give us our slope of the tangent line, or our instantaneous rate of change.
So for the second question, or part B, it says estimate the instantaneous velocity at -1, 0, 0.6, and 1. So the method I used the difference formula, and I found the derivative of that point. But since there is no function, we have to plug in our x and y values. So for this particular point, we'll have -1 and 0.5 at most, or is -1 and 0, and then we would plug that into the difference quotient and solve, and to get our instantaneous velocity. And these are like our answers for each point, and that's what I got when I plugged in the difference formula.
Okay, so finally we're gonna say some conclusions about our derivative. In the range of times from -1.5 to 0.5, we can see that our original function is increasing. Therefore, our derivative has to take positive y values. So since I did not use the values that Lawrence calculated, like he estimated, my graph will be just an estimate. But if we want to be more exact, we can use those points and just plug it in, and our derivative function will be a little more precise. Just going on to the second point, the second range, from -0.5 to 0.5, we can see that our original function is decreasing. So we know that our derivative will be taking negative y values in that range. And finally, from 0.5 to 1.5, our function is increasing. Therefore, our derivative will be taking positive values on the y-axis. And just to know what the meaning of p prime of 1 will represent, it would just represent the instantaneous velocity at x equals 1 in our original function. So Lawrence just said that at that point it will be 2. So we know that at that specific point, the slope of the tangent line will be 2. And that's just the meaning of what p prime of 1 will be. And that's it for our presentation, guys. Thank you for watching, and you may ask any questions after this.